In order to forward the frame to the destination, he's going to check the destination MAC address, which is a unicast address in the Ethernet frame received. If it's a multicast address, he's going to flood it to the port number of this multicast group. If it's a broadcast address, destination address is going to flood it all over the port, unless, but not from where it comes from. If the MAC address is not in the table, he can going to forward it, or we call to broadcast it all over the frame, all over the port, but not from the incoming port. Suppose we have the following address. We have A communicating sending a frame to D. A is connected to the physical port number 1. D is connected to the physical port number D. The switching, we suppose here that the switching table is already populated, is already learned with the MAC address of A, which is 000A, is connected to port 1, and 00D related to station D connected to physical port number 4. So when the switch receives an Ethernet frame from A, he looked to the source MAC address to update his switching table, either by adding it if it's not already within the switching table, or to update if the physical MAC address, the MAC address is coming from a different port number. Let's suppose A moved to port 2, so he has to update the switching table by adding 000A connected to physical port number 2. To take the decision to which destination port it should forward the Ethernet frame, he looked to the destination MAC address. Destination MAC address states that it's 000D. He looked up the switching table. He found the entry of related to this MAC address, which is connected to physical port number 4. So therefore, he is going to forward the frame from physical port 1 to physical port 4. In this video, you will be watching how a switch built his MAC address table and how he forward frame based on the content of their MAC address table. Kindly check the file within Teams. This is another video showing how the switch is going to behave when the destination MAC address or the source MAC address that are not listed in the switching MAC address table. In this lab, you will be completing two objectives. First one, to build and configure the network, and the second one, to examine the switching MAC address table, where Cisco called it a CAM table. The last section in this module, we will talk about the speeds of a switch and the forwarding methods used by a switch. To forward a switch, to forward a frame, a switch it has two methods. The first one called store and forward switching, and the second one is called cut-through switching. The first version of switches created, they used to call them bridge. They used to receive all the frame coming from a certain source. They have to memorize it in a buffer until they receive the last bit of a frame. Then they check the validity of the frame check sequence, which is calculated based on the CRC algorithm. If it's valid, which means that if the CRC calculated is equal to the one within the Ethernet frame, they consider the frame error-free, and they process the switch process to forward the frame to the destination port by checking the forwarding table or the switching table. If it's not valid, he has to write to drop the frame. This method was accurate when we used to have a network with error, contention error. It means with collision. Nowadays, with the new technology of switching, the collision is uh, let's say 0% available. Okay, so we have 100% collision free network. So we don't need to validate. We no more need to validate the CRC since there is no more error due to collision. So what we need, the switch doesn't need to receive the whole frame and to bufferize it. It will take storage plus it will increase the delay for the processing time. So they define a new method, we call it cut-through switching. You know, we saw in the previous slides that the switch need only two data from the Ethernet frame. It needs the MAC address source to update or learn the switching table, and he needs the destination MAC address to take the decision to which destination port it should forward this frame. So we don't need to wait for all the whole frame to take this decision. And if you see the Ethernet frame, the first address is the destination MAC address. So when he receives the destination MAC address, immediately he starts taking the decision, checking the switching table to take the decision to which destination port number he should transmit it, forwarded. He looked to the switching to the MAC address source to update his switching table, or even to add it if it doesn't already exist in the switching table. Then it will going to transmit it directly to the destination port. So the remaining of the Ethernet frame, it will not be bufferized, it will be switched directly to the destination port. This will enhance the quality of service for within a converged network, specifically when we have a converged network, which means running real-time applications such as voice over IP or video over IP data stream, which need high priority over web browsing traffic. For the cut-through switching method, in fact, there is two variants: the fast-forward switching and the fragment-free switching. So, as I told you before in the previous slide, once it gets the destination MAC address, it look up the switching table based on the port number associated to this destination address within the switching table. Immediately he start forwarding the frame. This method will have a the highest performance because it will not delay the frame, and you will bufferize it in the system, in the storage. The other method, the fragment-free switching, it's a compromise between high latency and high integrity of store and forward switching, and the low latency and reduced integrity of fast-forward switching. So the switch is going to store and perform an error check only on the first 64 byte of the frame before forwarding it. Why? Because it's the minimum size of an Ethernet frame, and there is a rule within Ethernet, legacy Ethernet, and first version of Ethernet, that a host should be transmitting while hearing what he's sending over the wire, and he compare what he transmit with what he's receiving. If that's the same electrical signal, so the source, he can consider that his frame is free from error. If he found that what he transmits is different from what he's listening on the wire, so he can consider that there is a collision, and he stop transmitting his frame, and he notify other station on the network by transmitting what we call a jam signal. So since the minimum size of an Ethernet frame it's 64 byte. It's enough to wait for the 64 byte, the first 64 byte of an Ethernet to check the validity of this information, to check there is no collision that occurred. In the fragment-free cut-through method and in the store and forward method, we need to store the frame before transmitting it, either all of it or part of it to the destination. So we need to bufferize this frame. So we need to know how to dimension and how much of the storage should be to avoid dropping frame. There is two techniques. First one, it's a port-based memory, and the second one is a shared memory. Example, if you go to a ticketing box in cinema, either you have all to be in line, the same line, waiting in line, in the same line, and then whenever a ticketing box is empty, you're going to be directed to the empty one. This is done in banking sector or even in some cinemas. Okay, this is what we call a shared memory. So all the frames will be deposited in a one waiting room, and whenever there is a port number or if you say time for this frame to be processed, donc يوصل الدور لهذا الفريم, the switch is going to start by processing this frame. Another method is a port-based memory, where every port, physical port, has a buffer. Then if you look up to a ticketing box office at a cinema, you see that people, they go, you can choose one line. Okay, for in front of every ticketing box there is a waiting room, okay, or a waiting line. Okay, usually once you get inside a line, you should not move from another one, even if there is empty ticketing box office, other ticketing box office. You have to wait in your you cannot move from one memory one line to another line, waiting line to another waiting line. In fact, in the theory of buffering, they found when they do mathematical analysis, they found that the shared memory is much more better and more performing than having a memory for every port. If you remember, in the first slide we talked about the first version deployment of Ethernet. It was over a coaxial cable, where we pulled the cable inside the room, and every host going to be connected through a connector or a transceiver, هو مثل الإبرة يعني, should be inserted within بقلب coaxial cable to reach the copper wire inside the coaxial cable. هون we had a problem, you cannot transmit and receive at the same time, otherwise you will have collision. So every station has to transmit, wait for a certain time before receiving a reply. This is we call a half duplex mode. Nowadays, with the copper wire, and since they are using two different pairs for transmitting and for receiving data physically over the copper wire, we don't have a problem of collision over these wires, so we can transmit and receive simultaneously, and we move to full duplex. 10 and 100 megabits per second Ethernet protocols, they can support half duplex on full duplex, while gigabit Ethernet ports, they operate only in full duplex mode. In practice, how a switch can tell the other switch if they are both running full duplex mode or half duplex mode. Okay, since they are over gigabit Ethernet, it's already they use only full duplex mode, but when running over 10 and 100 megabits per second, they can be differently configured as full duplex or half duplex. So here to avoid the problem, we as a switch, the IEEE, they defined a protocol called auto negotiation process, which permits for these two switches before starting communicating, exchanging Ethernet frame, to communicate together to set the type of duplex mode and the speed of the Ethernet port. So always we start with the best one. If both they support full duplex, so we go on full duplex. If one support full duplex, the other half duplex, so they lower down to half duplex. This is a auto negotiation between these two devices. So the best practice is to configure both Ethernet switches to run as full duplex mode. When connecting switches together or a host to a switch, this equipment we use usually different type of cable. You remember we talked about thread-through cable, crossover cable, and console cable or rollover cable. Rollover cable is used to connect a PC or a laptop to the console port on the switch to configure it for the first time, while a straight cable is used to connect a DTE to a DCE, and a crossover cable is used to connect between two DTE or two DCE. So when you connect a host, a machine, a laptop to a switch, you're connecting a DTE to a DCE, where the switch is a DCE and the host is a DTE. You can rely on using a straightforward cable. While connecting two switches back to back, so these two switches are DCE, you need to use a crossover cable. They define a protocol, or you need a feature, call it auto MDIX, which stands for automatic medium dependent interface crossover. So the switch, where implementing this feature, he can detect if the connected devices to it it's a DTE or a DCE. And based on the type, if you're using only straight through cable, even if there is another switch connected to your switch, so internally you will make the crossover. This functionality is available on Cisco devices running iOS release 12.2 and later. You can enable it or you can disable this feature, but you have to be careful when it's disabled to use the appropriate cable. Here we reach the end of our module. There's a summary of the main topics discussed and main information that you should be understand. You should understand and learn this module, and you can do the quiz at the end of this module to check if you got all the information.